Hello, my name is Isaac Cheney, and today we will be learning about electrophilic addition and elimination. So, to introduce these concepts, we must first review the characteristics of a chemical reaction within organic chemistry. And in chemistry, chemical reactions follow a set of elementary steps that are occasionally combined for larger reactions. So, in the reaction, we're going to start out with our reactants and eventually get products by the forming and breaking of bonds in the reaction. So here we have a hydroxide, and when you break the bond that's connecting them, you just get a proton, which is the hydrogen, and a very unstable oxygen there. So really, we can see a great deal of chemical reactions that happen just within the world that surrounds us, and so some common examples are combustion and the rusting of nails, photosynthesis, batteries, the reaction there, and even when fruits start molding. And so to go back to our chemical reaction of electrophilic addition and elimination, we have the flow of electrons from an electron-rich site to an electron-poor site, and this is how we form new products. And so the reason why we have this certain flow from rich to poor is because opposite charges attract and like charges repel. So it's unlikely that you would see the flow of electrons from a rich site to another rich site or a poor site to another poor site. And typically we see rich to poor most commonly is because an electron poor site has an unfilled octet of electrons that can be then filled by an electron rich site. And so, really, the breaking and forming of bonds is based off the flow of rich to poor. And so now we can add in our nucleophiles, which is an example of an electron rich site, right? So what a nucleophile is going to be an atom or a molecule that has an abundance of electrons, right? So this is usually showcased by a full or partial charge on the atom or molecule, but the abundance of electrons can also originate from pi bonds at the same time. And our electron poor site is going to be an electrophile, which is sort of the opposite of the nucleophile in that where the nucleophile has a full and partial negative charge, the electrophile is going to have a full or partial positive charge. And this is because they lack electrons, while the nucleophiles have an abundance of electrons. So now we can move on to our reaction. And first of all, we're going to be looking at electrophilic addition, and we're going to have a nucleophile and electrophile, and we can have two previous examples of that. But electrophilic addition is, like previously said, it's a common elementary step. So we can see that our nucleophile and our electrophile are going to be our reactants for this chemical reaction. And we can see the nucleophile has an abundance of electrons originating from a nonpolar pi bond. And the electrophile has two partial charges, one of them being positive. And so the abundance of electrons represented by the pi bond in the nucleophile is going to be attracted to the partial positive charge of our electrophile. And so when we have that attraction, the pi bond essentially is going to sort of break and grab the proton from our electrophile and form a bond with it. Meanwhile, the chlorine connected to our proton is just going to break away since it has that negative charge. And now we can see the products of our reaction. We have a carbocation that has formed out of the reactants. And a carbocation is a positively charged carbon atom. It is typically very unstable and only exists for a little bit, but it readily forms bonds to remove its positive charge. And then for our other product, we just have the lone chlorine atom, which is now negatively charged as it has lost a bond and gained two electrons. And to summarize electrophilic addition, we are taking an electrophile and adding it to a nucleophile. And the important thing to note about electrophilic addition and also elimination is that in addition, you're always going to have a nonpolar pi bond that is forming a bond with the electrophile. And in all types of reactions, energy is either released or absorbed. And this is based off the fact that bonds between atoms are formed and broken, right? So bonds store energy, so they must release or absorb energy to be broken or formed. And all elementary steps have unique free energy diagrams, like the one we're looking at right now. And these diagrams showcase the level of energy within the reaction as the reactants slowly form products. The reaction coordinate represents time as the reaction occurs, and the free energy represents the amount of energy in the reaction at any given time. And so now we can place our reactants onto the diagram, which are going to start at a low energy level. And then for our products, they're going to be quite considerably higher energy than our reactants. And this is because our products are noticeably less stable and therefore higher in energy than our reactants. Our products are also less stable because they contain a carbon that lacks an octet that can also be seen as a carbocation. And so now with our reactants and our products placed onto the diagram, we can jot down this trend line that showcases the movement of energy as the reaction occurs. So at the top of our trend line, we see a curve, and this is where the reaction reaches a point where the reactants are halfway to forming the products. And this point is known as the transition state, which has partial charges and a couple partial bonds. And these partial bonds are represented by dashes since they have yet to form or break during the reaction, but eventually will. And so now we can look at the reversal of our previous reaction, which is electrophilic elimination. And because carbocations are extremely unstable, the reversal of electrophilic addition is performed. And so here we see the carbocation as our reactant, which eventually is going to have a proton taken away from it. And the proton sort of represents our electrophile that is being eliminated, right? And so when you have that removal of the proton, the bond that it had to the carbon is instead going to be switched to a nonpolar pi bond between the two carbons in the molecule. And so now we have the free energy diagram of our electrophilic elimination reaction, which has our reactants starting at a high energy level since they're relatively unstable, and our products at a low energy level because they become relatively more stable and are therefore lower in energy. And so now we see that similar trend line flow, which flows from the reactants to the products. And then we also have our familiar transition state, which is relatively similar to previous transition state. So, what is the real world application of these two reactions? And electrophilic addition is actually involved in the production of ethanol. And ethanol is an extremely important organic compound that plays a pretty much a vital role in our lives. It's a main ingredient in most hand sanitizers since it kills bacteria and viruses, but it's also mixed in with gasoline fuel to reduce carbon emissions. And so ethanol is produced via a hydration reaction, which involves electrophilic addition. And a hydration reaction is any reaction where a molecule combines with water, right? And so in our case, sulfuric acid is used as sort of a catalyst in this reaction. And this is where the electrophilic addition takes place. So we have an ethylene here that has a nonpolar pi bond, and the pi bond grabs the proton within the sulfuric acid to produce an ethyl. And then our ethyl that is produced from the ethylene reacts with a water molecule and another elementary step, which is called a coordination reaction, where we have the oxygen attaching to the carbon. And that's how we end up producing the ethanol with a proton byproduct from the water. So sometimes these reactions can be a little bit hard to grasp within my head. So I like to imagine a funny little scenario that helps me really understand it in a different kind of way. So I imagine there's a farmer, and on this farm, he's got a faucet. And in our case, the faucet is going to be our nucleophile, right? Because and the water is sort of the electrons, and it has that abundance of electrons. And then the farmer also has a bucket, and the bucket is empty, right? So it has a lack of electrons. So in this case, the bucket is our electrophile, right? So once the farmer puts the bucket under the faucet pours water into the bucket, and the bucket becomes filled. So this is like if when the nucleophile and the electrophile meet, and now you have that sharing of electrons, right? And so really adding the water to the bucket is more of the electrophilic addition, right? So the bucket is the electrophile and we're adding it to the water. The reverse, which, electrophilic elimination would just be to remove the bucket from the faucet. And maybe the bucket has a hole at the bottom, so the water starts leaking out and it's returned to its electrophilic state. And so with that final analogy, that brings everything to a close. And at the end here, you can see my list of references. But thank you very much for listening. And I hope you learned something today. And have a very nice day.